All right, so the next kind of group I'm going to go over is this one where we're looking at a sample difference, okay? So here we've got calorie consumption before and after they're posted at McDonald's. We have the same 42 individuals, so we can create this difference variable. We find the mean difference is -50. The variance on that difference is 22,500. And we've got some hypothesis tests we're going to run. So here, my alternative hypothesis, and now on the exam, I wouldn't write this as H1. I'll make sure that I'm only using that notation of HA. We've got a less than sign of the alternative hypothesis. We have a left-tailed test, okay? I found a sample difference that was negative. So if I go ahead and look at my formula sheet, I'll kind of see, here's my test statistic when I have a mean difference. Now, because it's -50 here, and the denominator of a test statistic always represents a standard deviation, we know our test statistic should be negative as well. So we could actually rule out B and D here. From there, it's just a matter of we're going to have to plug those values in. So we've got that formula sheet that tells me, if I can, probably need to zoom in a little bit more here. Never mind. So let me make this a little bit bigger so we can see this. So I take that sample difference, which was told to us to be -50, divided by the standard deviation, square root of that variance over my sample size, which was 42 people. So I'm taking the square root of all this. My guess is what we end up getting here, if we plug this into a calculator, is -2.16, but we'll just double check that here real quick. So what, -50 divided by the square root of 22,500 divided by 42. Sure enough, -2.16. Sorry about that ping in your ears if you're listening to this, by the way. So we got our test statistic. Now it says, assume that you found the test statistic was -2.5. What's the critical value? And do you reject or fail to reject the null? Well, we've got what type of tail test here? Left-tailed test. So right away, we know that that critical value is going to be negative. We're dealing with a sample variance on that difference variable. So we know we need to use the student t distribution. So for a left-tailed test, we're going to look up from that student t distribution, the critical value that gives us that desired alpha in the tail, okay? I'm already forgetting, did I say alpha was 0.05 here? Yep, right here, 0.05, okay? So we want alpha of 0.05 in that lower left tail. So we're gonna have this negative critical value. So this also goes, when I'm looking up critical values now, I need my degrees of freedom, but with these matched pairs examples where I have a before and after time period of the same 42 people, it's just n minus 1. So 42 minus 1 would be 41. So I go to that student t table. I know that, oops, the area that I want in the tail is 0.05 at degrees of freedom of 41. So 1.683. However, remember it's this left-tailed test, so it's that same value, but negative, okay? So -1.683, my rejection region is the area to the left. If I plot that assumed true test statistic that I was given of -2.5, that's clearly in the rejection region, right? So when I go back to the answers here, it should be -1.683, and I clearly reject the null. I'm definitely in that rejection region, okay? So the other two questions we'll go over here are going to be some linear regression ones. I might throw in some additional stuff here as well that I could ask you. So the very first one, so we've got all these variables: education, job experience, age, all measured in years, gender, which is a 1 if the person was male, 0 if not. And then our Y, or our dependent variable, is wage measured in dollars per hour, right? So we can kind of think about, even if we just want to have a good idea of what we're doing here, we're taking wage, right? I believe it's hourly wage. We're including all these other covariates or control variables. So age, experience, I already forgot the other one, it was years. So age, experience, and education. I didn't have to, as soon as I switched over, I remembered. Education, and then there's a gender variable. We'll just call it male to make it a little bit easier. 1 if they're male, 0 if not. So the first question asks, what's the interpretation on that coefficient for education? Well, if we look at education here, it's a little small, but 1.233. Okay. So the way we interpret any coefficient is a 1 unit change in the x variable. So 1 more year of education predicts the y variable goes up or down by whatever the coefficient is. So it goes up by 1.233 dollars, holding everything else in the regression constant. So holding everything else constant, an additional year of education is correlated with a $1.23 approximately increase in hourly wage. Okay. Now let's say I'd asked you to interpret the gender variable or this male variable, right? So the gender coefficient was 2.29. So that means if someone went from the 0 group to the 1 group, or a female relative to a male, we would expect their wage to go up by $2.29. Okay, so that would be the interpretation there. What if I had asked you to interpret the intercept? Well, the way we interpret the intercept when we have these multiple variables is the intercept, whatever value we see here, that's the expected or predicted wage if all of our x variables are equal to 0, right? Because if they're all 0, 0 times anything would just be 0, and all we're left with is that intercept. So here, it'd be a kind of a goofy interpretation, but somebody with 0 years of education, 0 experience, 0 years of age, and they are the 0 group for gender, which was female, their predicted wage would be kind of $8.6 per hour. So it's a little bit goofy because we never see someone like that, but it is going to be our starting point, kind of where this line of best fit, if you want to think about it, kind of extends from. I then have another question, which is, what's the test statistic for this age coefficient? So I might do something like this in the exam where I leave off the test statistics and say, okay, look, calculate that test statistic for me, which if we go to our formula sheet, is simply take the coefficient and divide it by the standard error associated with that coefficient. So for the age variable, that would simply be take that coefficient of negative 0.019 and divide it by this associated standard error with that estimate, which is 0.083. Looks like that's going to be approximately negative 0.229. If I go ahead and calculate that. Okay. So hopefully these test statistical equation or questions for the linear regression stuff should be very easy points. All you do is take the coefficient estimate, divide it by the standard error. And if we move this out of the way, you could actually practice and do this for every single variable here. Okay. But this is what it would look like maybe on the exam, right? You can't see them. So another question that I might ask you here would be something like, I won't make one up here real quick. At the 1% significance level, which variables can you reject the null for, or maybe said differently, have a significant relationship with wage? Okay. So here, all I'm going to do, it's the same sort of process that we've been doing with hypothesis testing, which is if that p-value is less than alpha, I can reject the null, which the null here is that every coefficient or every slope coefficient is equal to 0. So if I can reject that coefficient is 0, I'm really saying there's a significant relationship. So I go back, I look at this output, I can definitely reject I can't actually reject the null for the intercept, right? 0.03 is not less than 0.01. I can reject the null for education, so there's a significant relationship between education and wage. I can reject it for experience. There's a significant relationship between experience and wage. I can't reject it for age, so I can't say that there's actually a significant relationship there. And I can't actually reject with that gender variable as anything other than 0. So there's not a significant relationship between gender and wage in this example. So that's another question that I potentially could ask you. Something else I might ask is, what percent of the variation in wages are explained by the, I actually probably list them on the exam, are explained by education, experience, age, and gender? Well, that's literally the definition of our R squared. The percent of the variation that we can explain in the Y variable, which is wages, by all of our included X variables is just up here at the R squared. Now, R squared is given to us as a proportion. So if I ask for the percent, 0.3685 would just be 36.85%. Right? So you look at that R squared, that tells you the proportion of the variation explained. If I ask for it as a percentage, you just move the decimal point 2 places. Okay. So those are some additional problems. If you're watching this on linear regression, I'll get all of these videos kind of posted in small segments as you're reviewing for the exam.